Hello, everybody. And I would like to thank the organizers for this really great event and for giving me the opportunity to present work I've been doing over the past 3 years, roughly, on primordial black holes in general and their potential role as dark matter candidates in particular. Of course, this is not work I've been doing only by myself. In fact, the field is probably 40 to 50 years old. And one of the key persons, which I'm delighted to have him as a collaborator, is Bernard Carr, who is probably the godfather of primordial black holes. He was not the very first one writing papers. I think it was by Novikov and Zeldovich, but shortly after, when he was doing his PhD with Stephen Hawking in the early 1970s, from that on, he wrote, I think, more than 100 papers to date, so he's very knowledgeable. I also work with Sébastien Claes, who is a researcher in Louvain-la-Neuve in Belgium, our beloved Katie in Stockholm, and Shun in Austin, Juan Garcia-Bellido in Madrid, Glenn Starkman in Case Western, and Luca Visinelli, who happens to sit here as well. So, all right, so, primordial black holes are in particular black holes. And one interlude, I have to say, this talk will be probably a bit more theoretical than the previous one, just to warn you or to frame it. So, and if you talk about black holes, well, the first thing you like to talk about is the formation. Now, well, we know about black holes in the galaxy. In our galaxy, we have a black hole of roughly 1 million solar masses. We know of black holes probably, of up to 10 billion solar masses, roughly. And by stellar collapse, we have basically lower bound of roughly a solar mass, but I guess a solar mass would be even already challenging to produce. So, but it cannot go lower. Now, you may have heard about primordial black holes of way, way lower mass, and let me tell you how, one can motivate or can intuitively understand how this is going to be formed. Now, let us very naively look at these objects, black holes, as they occupy a certain volume in space, if you refer to the Schwarzschild surface, and then have a mass. So I can roughly or naively ascribe a density, which goes like the inverse square of the mass. So higher densities correspond to smaller black holes, right? And when we now look at times when we have had large densities, it was actually at early times. If you look at the cosmological density, here's a function of time. So at early times, you can easily see at some point the average Hubble patch had a density which was comparable to a solar mass black hole, or even if you go at earlier times, it was at higher densities. And that's precisely the idea. So you have, in an already very dense environment, a perturbation that then collapses to black holes. Now, actually, this is happening at very early times. So one handy thing to remember is that around the QCD phase transition, the mass contained in horizon patch is roughly a solar mass. Right? And that is roughly a measure for what the black holes have as their mass. There's much more to it. There's critical phenomena and all these things, but that is roughly a measure for this. And also another characteristic mass for black holes is this 10 to the 15 grams, which is the mass of black holes which have roughly the lifetime of the universe today. So they would evaporate in the present epoch after their formation. So they are produced at 10 to minus 23 seconds after the Big Bang. So all of this is really produced deep in the radiation-dominated area. So it's produced very early. Usually primordial black holes are referring to black holes produced around the BBN. All right. So, and there's several formation mechanisms, and I give hour-long talks about each of them. So let me just briefly sketch. You can have closed loops of cosmic strings that have enough energy density to collapse to a black hole. You can have, in first-order phase transition, you have nucleation of bubbles. The bubbles may collide, and in certain circumstances, you will have also large enough energy densities to form black holes. One must say that these scenarios are not so much considered anymore because it seems to be rather baroque. You have to tune a lot. There's one interesting aspect, and I will talk more about this, is if you have, for instance, the QCD phase transition or in general phase transitions, you have a change in the pressure. of the background fluid, of the radiation fluid, and that makes it potentially easier or much easier to form black holes. And well, in most scenarios that people consider, you have the collapse of inflationary density perturbations. So, and Bernard Carr was the first one to make a simple estimate to relate the medium. So he assumed some perfect fluid, so P equal W rho, and so in radiation we would have a third. So he calculated by just comparing the Jeans length to the scale of the overdensity, above which density contrast, so delta's density contrast, so delta rho over rho, above which density contrast you initiate a collapse. And that's just assuming a top hat overdensity. And he said what he found is basically, on a relatively short calculation, that this is basically related to the equation of state parameters. So if you lower that one, you would lower the threshold, and hence you would increase, or even decrease if you increase the omega, the primordial black hole formation rate. Now, how does it setup look if you look at the time of the universe and if you look at scales involved? Now, here I put physical scale or scale, and here I put time as a function of number of E-folds. You have a period of inflation. That's the Hubble scale. This gray line is the Hubble scale, and it's roughly constant during inflation. Then you have, it increases during radiation domination, meta domination, and then followed by something that looks like a cosmological constant. Now, if you have a scale, a physical scale, that would leave the horizon and re-enter at some point later, and if the threshold is bigger than, or if the density contrast is bigger than the threshold, you would initiate a collapse to a black hole. And note that if you have a scale that leaves earlier, it would re-enter later, right? All right. And one other thing to note, that's a slide I took from a talk by Chris Burns. So if this is a primordial power spectrum, this axis, and this is, again, the number of E-folds, note that the scales we are talking about, because you need rather large values of the primordial power spectrum, that this is at far, far smaller scales, many orders of magnitude smaller scales than the scales we observe in the CMB. So you can have models that have this nice power law, and then you have some feature at way, way smaller scales. And also note that these are basically very rare events. So you are very deep inside the tail. Actually, typically you are talking about 10 sigma fluctuations, and this is exaggerated, so it should be much, much further further down the tail. And you also note thereby that basically, since you're very deep inside the tail, you're very sensitive to non-Gaussianities. That's also an issue of research. And one thing what I want you to take away from that slide, besides that we talk about rare fluctuations, that the amount of primordial black holes, which is often characterized by the fraction of collapsed horizon patches, which is denoted by beta, that depends exponentially on this threshold. So if you change the equation of state parameter by a little bit, you may change, or you do change beta by potentially orders of magnitude, right? Good. That is, I must admit, an outdated graph, but still a graph that I like to show because it shows sort of constraints at the time of formation. Here we have basically beta rescaled by the relativistic degrees of freedom. So it's basic measure for omega PBH at the time of formation. Note that these small numbers on that scale, and this is versus the mass. And look, these primordial black holes could exist potentially over a huge range of scales. Here's a Planck scale that goes way up to 10 to the 50 grams. And I can't talk about all these constraints. I just want to say that the strongest constraints we get from those that evaporate today, the black holes, is they would emit by Hawking radiation, gamma rays, and which we do not observe. They got very strong constraints. In this graph, at this time, there was no constraint here. But even if you think about primordial black holes make up 100% of dark matter, you are at collapse fractions of you have every 10 to the 15th horizon patch is undergoing a collapse. So that is a very, very rare event that is happening, and even more rare that you have two close to each other. So you wouldn't have objects that merge very quickly because it's very rare to find even one. And also note that that primordial black holes are created in a radiation environment, but there are matter, so there's a different scaling, and that means their relative abundance is boosted significantly. That's why these small numbers here could make up 100% of dark matter in these objects today. And since I talked, they exist on a huge number of scales. They interfere or they influence a huge range of physics. So I can't possibly talk about all of those. I can briefly sketch it. This line is the line of evaporation. So if you believe that Hawking radiation holds true, there's some research going on about this. But if we take this as more or less established fact, then those above this line that are lighter than 10 to the 15 gram have already evaporated or evaporating at the present epoch. In the early times, they could change, BBN, they could reionize the universe, they do all sorts of things. But those that are heavier than the 15 grams basically have a gravitational effect, or most dominantly a gravitational effect. And I'm most interested that they could be the cold dark matter. They emit, of course, gravitational waves. They could seed the supermassive black holes in the galactic nuclei, manifest themselves through lensing effects, and all sorts of different signatures which you could study depending on the mass range where they exist. Now, let me give you a number. I find it illustrative to make the following consideration. So if you look at primordial black holes of 10 to the 20 grams, and assume all dark matter is made of these objects, 10 to the 20 grams, they would have a size of 10 to minus 8 centimeters. 10 to minus 8 centimeters is the size of a hydrogen atom, right? And the distance would be 10 astronomical units. That's not what you would call a high density. It's a very sparse set. And of course, if you go up with mass, you go, of course, up in distance. All right, observational conundrum. There's many puzzles we have today, and let me list, or many observations which we may link to primordial black holes, and due to the time constraints, I can't possibly go through a whole number of them, but early this year in Chile, there is actually the Warsaw University telescope is 1.3 meters. It's a relatively modest telescope, as I understood. I'm not a very much of an experimental or observational person, but this seems to be not a giant one. And so there was a paper these days, or in early this year, we did a reanalysis of the OGLE data, and they detected, different microlensing populations. One population had a microlensing light curve timescale of 1 day to 300 days, and they basically know what this should be. So this could be should be brown dwarfs, main sequence stars, white dwarfs, Newton stars. So they have a fairly good understanding what this could be. But also, OGLE detected another population with a timescale of hours, and they basically, or it's basically unknown what the origin of this is. And one speculation could be that this is free-floating planets, but you would need so much to explain that. And I will show you soon how much you actually need. That the best guess of that team is primordial black holes. And look at this. So here we have the fraction in dark matter fraction in primordial black holes, so omega PBH by omega dark matter, versus the mass in here's above you have solar mass, then you have grams, and that is some by another microlensing survey, HSC, some excluded region, and this is a region compatible with data which is actually the best fit that they have. We have about few percent, probably 2% of the of black holes in planetary mass, 2% of the dark matter and planetary mass black holes. So, and this amount to have in free-floating planets is probably unfeasible. That's I found quite interesting. And another thing is very different topic. So primordial black holes start, as this in originating from this density perturbation, as I told, from inflationary origin. Now, we have this big overdensity. It sometimes, at some point, fits in the horizon. and it starts in a non-spinning way. There's no rotation, and you would not expect a lot of spin. I mean, of course, there's the accrete, there's perturbations, but you would not expect a huge amount of spin. And actually, if we look at LIGO data, then it looks like that when you have a look at what they call effective spin parameter, which is basically a weighted sum of the individual spins projected on the angular momentum of a binary system. That's a binary black hole merger. And there's, of course, there's huge error bars, as you can see, but it looks like that those from those known events, 11 of these are here, they have either compatible with 0 or with very low effective spin parameter. It's not a proof for primordial black holes, but I think it fits into this picture. All right, and then is something I lately, or which I wrote with Bernard Karl, Sebastian Kless, and Juan Garcia Bellido about, because we are very excited about the connection of fundamental physics, so besides inflation, but fundamental physics, in terms of the thermal history of the universe, and primordial black holes, and solutions or resolutions of some cosmic observational conundrum. So, and we are so excited, so let me just call this probably a thermal history mystery. Well, actually, but by the way, how much time do I have left? Anyway, so I keep talking. Oh, perfect. Thank you very much. And so here we see the relativistic degrees of freedom, and here we see the temperature of the universe in MeV. And as the universe expands, the temperature cools down. The universe cools. The temperature goes down. The universe cools, and time goes in that direction as well. And at some point, more and more particles become non-relativistic. So you have the top quark, have the W&V boson, have the proton, have the pions, and electrons. So, and this changes several events that change then the number of degrees of freedom. And every time you have a stark change of this, you also change the equation of state parameter. So that is denoted here as a function of temperature as well. So again, put down the masses here that become non-relativistic at these temperatures. So, and you have, at higher temperatures, you have this tip from the electroweak phase. Then here we have the QCD phase transition, the pion plateau, and we have here E plus E minus annihilation. So, and this is basically, here's the third. So you have basically, it's radiation, perfect fluid with radiation, equation of state otherwise, but here you have, you have some dips. You see, well, this is doesn't sound like being so much. It's still, of the order of, what is it, 10, 20, 30% maximum. So, but I told you at the beginning that the abundance of primordial black holes depends exponentially on the equation of state parameter. So beta is this fraction of collapsed universes is collapsed horizons is exponentially depending on the threshold, which is determined, which is also closely connected to W. Now, and that is basically what we found. So in this model, basically, you start with something featureless. You have a power law density spectrum. You come in with a very slight tilt, like 0.97. And so you start with something which is basically flat, basically featureless. And no, this I found very striking. So the scales involved, so when we go, let me go back. So the scales involved, when different events in the universe happen, the thermal history. Yeah? Here from the electroweak, the QCD, and E plus E minus annihilation, they correspond to scales that are relevant to observational facts, so or curiosities or conundra. Now, if we start with, and we have to say that the horizon mass increase, so time goes in this direction. It's just the if you go back. So that's lower masses and that's higher masses in that range. So, and if you start with something and the overall mass function gives you 100% of dark matter, so that's giving you, this provides the entirety of the dark matter in primordial black holes. That is giving you 2% in black holes in the planetary mass range, so those that are detected by AUGO. Then you have, black holes that are compatible with the merger rate you observe in LIGO. And it also provides seeds for the supermassive black holes in the galaxy. And this is really, I can't stress it enough, I find it really so fascinating that these scales, they're already, linked to the fundamental physics we see by the expansion rate. So I find it very, very interesting. And there's also, it's many thanks to Sebastian Kless, who calculated the likelihood, merger likelihood of two black holes with mass M1 and M2 here in solar masses. And most of the black holes LIGO measured are really lying in that region. That is already incorporating the LIGO sensitivity. But also note that there should be an enhancement, there should be, soon we may measure, it's a prediction of the model to measure also low mass ratio mergers. So, or I don't know whether they call it high mass ratio or low mass ratio, but mergers with different, depending on how you make the ratio, but, different mergers of different masses. And so that is a prediction of that model. And let's see whether this will come through. And I think 03 run of LIGO may tell us more about this. Now, I told you before that, well, I have somewhat, a density spectrum which has an amplitude which is somewhat enhanced, and it's basically featureless, and all the features are coming from the thermal history of the universe. But of course, another question is how to basically get the enhancement, how to create enough power to incorporate, to actually make enough black holes. And so we have to talk about enhancement. I will talk about briefly about this. There's many mechanisms to do so. There's several inflationary models with multi-field inflation models, hybrid inflation, there's axion curvaton inflation. There's many models and many people worked on this, but what lately came into a consideration is what's called quantum diffusion. So now, suppose you have a single field inflation model. So here's the inflation inflaton potential, and inflaton is denoted by phi. Phi is on this axis, and you have phase of slow roll, and towards the end of inflation, you have a plateau-like phase. Yeah? So classically, what would happen, now that's the classical equation of motion, that this side equal to 0. So if that potential drops out, right, you would get an exponential solution for phi, and that would really exponentially increase the power spectrum. Now, of course, in this case, you do have much more than just the classical evolution. You have quantum effects. And together with Katie, I was doing some research on how the effect of such a plateau can be on primordial black hole formation. And I must say there are other papers on this as well, for instance by Tony Riotto and collaborators, by Juan Garcia Bellido and collaborators. But we were incorporating non-perturbative methods to see how much of an enhancement we get. And you actually do get quite a large enhancement. So let me explain what you see on this figure. So he basically, for this figure shows you the fraction of collapsed universes. Once in a classical configuration, if you just take the plateau and look how much the amplitude is boosted. For different length of the plateau, the different colors indicate different lengths of the plateau. And this is if you take this quantum diffusion into account, the quantum effects into account. And we have some, it's more technical, I don't want to go into this technical detail, just mentioning that has to do with what is called Feynman-Jensen variational method and replica field theory. And you see that this sort of, something called a dental plot, looks like a tooth. So you get a very strong enhancement already from the quantum effects. So you have in this type of potential, you don't need necessarily a very contrived scenario, but of course now you have to see how long the plateau is and how this is exactly coming about. It's not yet a fully complete picture, but it points in a direction that by a single field inflation scenario, you may enhance the spectrum potentially enough to create primordial black holes, sufficient amount of primordial black holes, and this then, if it's at the right place, could, together with the thermal history of the universe, explain the dark matter and several observational conundra which we have. Now, let me conclude. So I find, and I hope to convince you, that primordial black holes are very interesting objects, and depending on which scale they exist, they interfere with almost all kinds of physics that you can find in the universe. And I pointed this out multiple times, that especially during extended range of scales from, say, about planetary mass up to billion solar masses, the thermal history of the universe encodes the scales which which point to or may explain observations that we made. So, and concretely, all at the same time could be explained all of these points. So this orbital microlensing events, its planetary mass, LIGO gravitational wave events. Then you have the seeds for the supermassive black holes and the galactic centers, and could be all of the dark matter. There are more things. There seems to be an excess of dark lenses. There seems to be, or there appears to be measurements of quasi-microlensing events which cannot be quite explained, so that can incorporate for this. We checked this, there's more points, but I wanted to list what I thought are the main points and the most convincing points that this scenario could account for. And the enhancements which we need may come naturally from quantum effects. So if you have just a simple plateau close to the end of inflation, that may boost the power enough in order to produce primordial black holes. So with this I close, and I thank you for your attention.